Welcome back. So the final section of chapter 1.9, at least that's what we're looking at. So we'll be looking at inverse functions, and we had a little taste of it at the end of 1.8. So we saw that when we composed specific functions, we got a really unique conclusion out of those. So we'll come back to that in a second, but let's first just define what inverse functions are. So if we have a very simple function, f of x equal to x plus 2, and let's restrict the domain and range a little bit. So if we said that it started with inputs from set A of 1, 2, and 3, and we mapped them to set B, which would be values of 3, 4, and 5, we can say that f of x should be equal to this function. So x plus 2, but specifically restricted for this domain and range. So we get these three ordered pairs. Now, what happens if we've swapped those ordered pairs? We swap the values in those ordered pairs. So by interchanging the coordinates, we obtain the inverse of the function f, which is written f with a little exponent of a -1, and it's right next to the f. So f inverse is a function from B to A. We reverse the order of those numbers. So now we can see that our ordered pairs just get reversed. So 3, 1, 4, 2, 5, 3. But now the question is, what should the function look like? How would we get from 3 down to 1, from 4 down to 2, 5 down to 3? Well, we're not adding 2 like we did here. We are doing the opposite. And we're subtracting 2. So x minus 2 should be the inverse of x plus 2. Okay, it seems like it makes sense and it's pretty easy to grasp, but how can we show it? How can we verify that that's truly the inverse? And the question is, what happens if we compose them? So, if we compose f with f inverse, let's see what we get. So f inverse we said is x minus 2. So now we want to plug this into our function f. So we should get x minus 2 plus 2, which we can see equals x. All right, let's go the other direction just for the heck of it. And you can probably already guess that it will behave very similarly, and we get x in that direction as well. And that's going to be the condition that is satisfied when you have inverse functions. So we should always get that composition in both directions to boil down to give you x, if they are truly inverses. So that's how we're going to define it. So the definition, f and g are two functions that have this happening, that the composition of f with g is equal to x, and the composition of g with f is equal to x also. And when that happens, we can say that g is the inverse of function f, and we can call it f inverse. And so the domain of f is equal to the range of f inverse, and the range of f is equal to the domain of f inverse. So remember, those two sets swap. So that's why we say what we're saying. So now, how do we find inverses in general? In some cases it will be easy. So, the x plus 2, x minus 2, that seems pretty easy, right? But what about f of x equal to 4x? What do you think the inverse of that's going to be? How can we undo that process? Well, we can see that we're multiplying by 4 here. So let's think opposite. Let's divide by 4. So we think that the inverse function should be x over 4. Well, it's probably right, but let's check it. So if we compose f with the inverse to start, we're going to replace that f inverse with x over 4. And now we're going to replace our x in our function f. And we can see the 4's cancel and we have x. All right, let's go the other direction just for the heck of it, but not really. So we want to replace f of x with 4x, and then we can plop that into our x in f inverse. And lo and behold, we get x again. So it checks. All right, so that was an easier one. Well, we're going to see how to get more complicated ones in a minute, but let's do another verification on something that's a little bit tougher. So this one's got a little bit more substance to it. So we got f of x equal to 1 minus x cubed, and we got g of x equal to the cube root of 1 minus x. So again, the order in which these cancel out to give you x is going to be reversed when you go one direction versus the other. So let's verify that. So let's start with f of g of x. So we want f of the cube root of 1 minus x. And so I'm going to go right down below here. So we got to plug this input in for x in function f. So be really careful how you write this. So we want the cube root of 1 minus x, but then we got to cube that. So what are we going to cancel out first? Well, cube and cube root, that's really going to trump everything. So let's cancel those out. And now let's be careful how we write the rest of it. The parentheses are not gone. The cube roots and the cubes are. So we're going to keep those parentheses, 1 minus x. And now we can see why. Because when we distribute, that makes that x a positive x. And now the 1's cancel, and you're left with x. All right, let's swap it around. So we want to replace f first, so g of 1 minus x cubed. So we want to replace our x with x minus x, 1 minus x cubed in function g. So we need that cube root. We got a 1 minus, and now that input of x is replaced with this. So let's use parentheses around it. So that should be the proper format. And so now, how do we proceed? Cancel out the cube and the cube root. We got to get rid of those parentheses first. So let's distribute that minus through. And now we can see the 1's are going to cancel first. Again, opposite order. We canceled the 1's last, so we should cancel them first, the other direction. And now the cube and the cube root are going to cancel, and we're left with x. So that is a little taste of inverse functions. We're going to see some more examples in the next video, so stay tuned.